Hi everyone, I'm Nasrullah. With me is Berthold. We are from IBM Research, and we are going to talk about how we bring vector search to Presto. So the general idea, the goal of this work is that how we can bring generative AI applications to Lakehouse, such as RAG applications, that is Retrieval Augmented Generation, in which we retrieve the relevant data from the Lakehouse and feed it to LLMs for generating the answer and along with the source. The second thing is how we can run the hybrid queries. The hybrid queries are in which we jointly query the structured and unstructured data which is in the Lakehouse. For example, you want to search for sandwich toys, which has a filters like, you want it to be between $10 and $100, and the rating should be more than 4 and with free shipping. You see that in this query, you have two parts. One is unstructured part, that's the sandwich toys. You want to do the search on sandwich toys along with the filters, which is the structured data. So we want to run this generative application on Lakehouse such that we want to use the power of SQL on all Lakehouse data to provide sophisticated input to LLMs. And second, we want to have a separation between vector databases and the relational data. In vector databases, we will only use it for vector indexing and the similarity search, and we run the relational filters in the Lakehouse. It will help us to avoid the unnecessary data redundancy into the vector DBs. And more importantly, it will also help us to preserve the data governance. So if you have the security and access controls on the Lakehouse data, you don't need to worry about them on the vector DBs because it's only storing the vectors. So we need to bring, all of these applications are dependent on the vector search, so we need to bring vector search to the Lakehouse. So the first thing, I will just introduce what is vector similarity search. So vector embeddings are the latent representations of data in a low-dimensional space, and vector search helps us to find the nearest neighbors to a given query vector. For example, you have a query you want to search for sandwich toys for kids. First, you will obtain the embedding of this model using an LLM or any embedding model, and then we'll give it to the vector DBs, which has two components. One will be the embedding store, which will basically indexes the data using, say, for example, IVF flat or HSW indexing, and then you will have the vector similarity engine, which performs the similarity function. It can have a similarity function like Euclidean distance, and then it performs the nearest neighbor search and gives you the top k relevant results to your vector query. The second thing is what's the Milvus? We are using Milvus vector databases. It's a very high performance vector search. It performs 7,500 queries per second on a 12-core system with 16 GB of RAM. It supports multiple types of indices like a flat, IVF flat, or HNSW. And it defines a vector database. It has two components. One is the fields, and second one is the index. So these the fields and index, they are called as the schema. For example, here we have one of the schemas. There's a Walmart schema, and you can see that it has two fields defined here. One is the ID field, which defines its unique key, and second one is the embedding embedding field type, which is of data type float vector, in which you have to also define the dimensionality of this float vector. And along with these schemas, you also define the indexing on this type of the embeddings. Now the point is, how do we connect our Presto with the Milvus? We have built an HTTP-based Milvus connector, which enables it to run the vector search queries. So the query is transformed into an HTTP request and sent it to the Milvus, and Milvus returns you the IDs of the top key similar items. So you can see that we have a separation between the Lakehouse data and the embeddings. Say, for example, on the Lakehouse side, we will have an iceberg table. It is a Walmart data set. It has ID. It has the fields of ID, product name, and the description and other fields. And first, what we will do is that we will take one of the fields, say, for example, the description field, obtain the embeddings, and load those embeddings into the Milvus storage index, and we will index these embeddings. Now, since now we have the embeddings, we have the data on the iceberg side. Now we should be able to run the hybrid queries. If you see the example here, this is a hybrid query. There are two queries basically. The inner query is a vector similarity query, which is sent actually to the Milvus to run the vector similarity. And in return, when you get the IDs from it, you perform the join on the table, which is the iceberg tables. So Milvus is used only for the vector similarity, and other relational filters are applied on the iceberg table here. So seeing some queries here, how we interact with the system. So if you run the show catalogs function, it will show you the Milvus as there. And if you want to see the schemas here, the more important point here is that there will be only one schema, that's a default schema. And if you want to list the tables, all of the vector schemas in Milvus are referred to as the tables in here. And if you want to describe any, the properties of any schema, we have the describe function here. And if you want to describe the fields or list the fields of any schema, you just have to put in the argument of the fields here. Now the important query here is a search query. This is the syntax of a search query. We define the vector schema name on which the similarity function is to be performed, and then the search function along with the arguments and how many top elements you want to get it. One important point is that this is a Milvus reference. It's evolving. It's not like fixed yet. So first thing that we need to do is that you need to extend the Milvus.properties file. We need to add embedding.uri is a service endpoint which you will use to get the embedding of your search text query. And the second one is a model ID, which model you want to use for that embeddings. Then simply you can run your search query here, right? So like select ID from Milvus.default, then the name of the table, then the search function along with the search query argument. And it will return you the IDs of top 10 similar vectors here. Now going back to the hybrid search query, how it basically happens is that you have two queries here. One is the inner query. The inner query is used to perform the vector similarity search, and the query returns the IDs of top k similar vectors. And those IDs and the outer query does a join on those IDs and applies the filters on the iceberg table, and then you get the output here. So it should have been 9 outputs, but now we are applying more filters, so you only get the 9 rows here. Now talking about the hybrid query performance, if you see the hybrid query, we have two queries. One is the vector similarity search, and other one is a normal query. So vector similarity basically increases your overall recall of your search query because it's a semantic query. It's not like an exact matching query. It performs a semantic search on the text data. And going back, we have two components. One is a vector search, and second one is a relational data search. So the time taken by the vector search is very small. If you can see here that we have 1 million vectors of 128 dimensions with 16 GB of RAM. We can have 7,500 queries per second. And if you have like a 1 billion vectors also, it takes only a few milliseconds for searching the top K in that. And other more important point here is that this vector search query has to return only a small set of values, that is the IDs only. It doesn't have to return a lot of data from the query. So all of this along make it like a very fast query. And then the major part is done by the relational data search, in which you have to perform the join on the IDs. So it has to scan a lot of data. So the major part of the time is taken by the relational data search. So overall, the vector search adds the minimal overhead in this type of queries. Yeah, thank you. Enjoy generative applications. Any questions? I'll be happy to answer. Oh, yeah, I'll be around here, so I'll be happy to talk about it. Thank you.